This is Chris with Dive Zone Scuba for another technical diving tips, techniques, and trips video. The purpose of this video is to instruct new technical divers in some basic technical diving calculations that they will encounter. If you are already an accomplished technical diver, you will probably find this video boring. Having said that, these will be the types of calculations that we'll be discussing in this video. The first calculation involves the MOD for gas blends. Here, what we're specifically looking for is what is the maximum operating depth for a particular breathing gas that has a given fraction of oxygen. Here we actually have two different types of calculations. The first one is for determining the maximum operating depth in a working condition, which means you're at the bottom or you're ascending to your first deco stop, and we'll use 1.4 ATA for that. And the second type is for calculating the MOD for a decompression gas, and we're going to be using 1.6 ATA for that. Different certification agencies may use different ATAs for different applications, but these are the numbers that we're going to be using for today. Here is the formula for calculating the working maximum operating depth in feet. Note that the fraction of O2, the FO2, is going to be a number between 0 and 1.0. It is not a percentage. So if you were using air as a bottom gas, you would not use 21%. What you would use is 0.21. The other thing to make certain of is that you take the 46.2 and divide it by the fraction of O2 before you subtract the 33. If you do not make the calculations in that order, you will obviously receive incorrect results. Here is the working mod calculation for air. So here we have 0.21 is the fraction of O2, and after calculating all this out, we have a maximum working operating depth of 187 feet. On a side note, you should probably not dive on air to 187 feet, although that is allowed by the MOD 1.4 calculation, and this is due to the effects of narcosis. Here is the formula for calculating the decompression maximum operating depth in feet. Here, the equation in the numerator in the first term is changed to 52.8, and this will account for the 1.6 ATA instead of the 1.4 ATA for the working MOD. Here's the calculation for the Deco MOD for 50% oxygen. So here we have the 0.50 for the FO2, and our MOD is 72.6. In most situations, the 72.6 is just rounded out to 70 for simplicity purposes. The second type of calculation that we're going to discuss is for ideal gas mixtures. Here, what we're trying to find out is what fraction of O2 or what percentage of O2 should be used for a particular depth. Here, we're making the assumption that we should use 1.4 ATA to minimize our decompression obligation during the working part of a dive. So what we're going to do for this calculation is we're going to take our basic working MOD formula and we're going to rearrange it, and instead of solving for the MOD, what we're going to do is we're going to solve for the fraction of O2. So again, we're using the working formula for the calculating the MOD, and we're using the formula with the 46.2. Here I'm rearranging the formula for solving for the fraction of O2. I'm going to break it down into two steps to make it a little more clear to see. In the first step, what we're going to do is we're going to add 33 to both sides of the equation. So now on the left side of the equation, we have the desired depth and 33 feet. And on the other side of the equation, we just have the 42.6 divided by the fraction of O2. In the second step, what we're doing is we're moving the depth plus 33 to the denominator on the right-hand side, and we're moving the denominator of the FO2 to the numerator on the left-hand side. So our fraction of O2 is equal to 46.2 divided by the total of the depth plus 33. Rather than trying to memorize this formula, it may be easier just to start with the one working MOD formula and derive the fraction O2 from that formula. Here is our calculation for determining the ideal gas blend for a depth of 130 feet. The 130 feet is inserted into the right-hand side of the equation in the denominator. The resulting calculation is 0.28 for the fraction of O2, or 28% O2. The next calculation involves partial pressure. Here, the primary thing that we're concerned about is determining if our planned gas is safe for our planned depth. Here is our formula for making the partial pressure of O2 calculation. We have the first term, which is the fraction of O2 in the mix, and then we're going to multiply that by the atmosphere's absolute at the depth that we are going to be breathing the gas at. When we use this formula, we are first going to have to calculate what the ATA value is. Here is the calculation for determining the partial pressure of O2 for air at 145 feet. We have inserted 0.21 for the fraction of O2, and we have also inserted 145 feet for the depth. This yields a partial pressure of O2 of 1.13. Since this is well below the accepted limit of 1.4 for working calculations, most agencies would consider this acceptable. The next category of calculations involve determining exactly how much gas I do have in my tanks. This is sometimes an issue because the fill pressure may not exactly coincide with the rated pressure of the tanks. This is an important issue as you really need to know how much gas you actually have in your tanks rather than just what the tanks are rated for. It is obviously unsafe to start a dive with less than the amount of gas that you actually need, including your reserve. In these calculations, we are going to use rated volumes for tanks, not the actual volume of a given size tank. For example, we'll use 80 cubic feet for an AL80 instead of 77.4 cubic feet, which is the actual volume, which varies a little bit between manufacturers. In reality, the same applies to probably almost any tank that is used for diving. Here we have two different possible situations. The first is where you have a set of tanks that are actually pressurized to less than the rated pressure. And then the second situation is where the tanks are actually filled to a higher pressure than the rated pressure of the tanks. Here is the equation for calculating the actual volume in the event that the actual pressure differs from the rated pressure. The first term is the total rated volume of all the tanks. Frequently, new divers, when making this calculation, forget to make sure that they double the calculation if they're using a twin set. The second term is the actual pressure divided by the rated pressure of the tanks. With the second term, it is clear that if the actual pressure is less than the rated pressure, that the second term will be a value less than 1. The total calculation will then yield a number which is less than the rated volume. On the other hand, if the actual pressure is higher than the rated pressure, the second term will be a number greater than 1. And the actual volume will be greater than the rated volume of the tanks. Here's a situation where a AL80 twin set is filled to 2800 psi. The AL80 twin set has a total volume of 160 cubic feet. This is multiplied by 2800 divided by 3000 and yields an actual volume of this underpressurized set of 149.3 cubic feet. Here is the opposite case where our AL80 twin set is pressurized to 3200 psi. We multiply the same 160 cubic feet by 3200 divided by 3000 and have an actual volume of 170.6 cubic feet. Please note that overpressure fills are not recommended. This example is for educational purposes only. The next calculation is END. This is what is the equivalent narcotic depth for a given percentage helium mix. The presence of helium in a breathing gas mix reduces the narcotic effect of both nitrogen and oxygen. So calculating the END provides the equivalent depth if you are not diving with helium. Depending on the activity taking place, some certification agencies will specify an END between 100 and 130 feet. END is calculated by taking the depth and adding 33, multiplying that by 1 minus the fraction of HE, and then finally subtracting 33. For a 200-foot dive with 30% helium, the END would be 130.1 feet. For a non-overhead environment, non-complex dive, 30% would be considered acceptable for a 200-foot dive by some certification agencies. So these are some of the basic calculations that you may encounter when enrolled in a technical diving course. This is not an exhaustive list of calculations that you may encounter. Some calculations, such as gas density, may be better calculated using decompression software. This is Chris with Dive Zone Scuba. I hope you found this video helpful. And thanks for watching.